we're going over chapter 13. For some reason, this was recorded earlier, but they never gave me the link. So I'm not sure if I did something wrong or they never sent it. So I'm pre-recording it again to leave it out for you guys. Chapter 13 is about peripheral nervous system. As you know, anything outside of the central nervous system is peripheral nervous system. Okay, so central nervous system was brain and the spinal cord. So this peripheral nervous system is all the sensory neuron that brings in information to CNS and all the motor neuron that takes out information from CNS. So basically, it's a way to connect with the external environment. Okay, so you can sense different things, and in a way, it will be able to communicate if the temperature is hot, for example, and that's external environment. All right, so what we're going to be doing is mostly going over the peripheral nervous system and the type of sensory receptors. If you recall, we mentioned that you're starting off with receptor, and then via the sensory neuron, information goes to the control center or central processor, and then via the motor neuron, it goes to the effector. So that's what we're going to be looking at. Mostly we're going to be looking at the receptor. Now, sensory receptors, they're coming in a lot of different types. And the idea is that sensory receptors, they trigger their action potential or impulses, and they send that information to CNS. Interpretation, making a sense of it, the perception of it, all of that happens in the central nervous system, in particular the brain. If the temperature is hot, that information goes into the brain. Your brain hypothalamus is able to figure out, for example, whether it's getting hot or cold. Next up, we wanted to take a look at how do we classify the receptor. If you go to a library, everything is classified based on different ways. Like, for example, books can be classified based on the author. Books can be classified based on the topic or the subject. So in the computer system, you can look up a book based on several different topics or author or the year, things in that nature. So there are different ways to categorize the receptor. All right, the books. Similarly, for the receptors, we wanted to be able to classify them so that way we can study them. One way of the classification is based on the stimulus type. How do they get stimulated? All right. So these are as follows: mechanoreceptors. Mechanoreceptors, they respond to touch, pressure, vibration, stretch, itch. So again, think about where you have those. If you're touching an object and so on, that's your mechanoreceptors. If somebody tapping you back wanted something from you, that's vibration and touch and pressure changes. Those are the mechanoreceptors. These mechanoreceptors could exist in your joints, your ligament. All right. So again, they could respond to the mechanically, they could get stretched, and as a result of that, or your body can do opposite action because you don't want it to, damage any ligaments or tendons and things like that. All right. So sometimes this is known as a proprioceptors. We'll discuss that later. What's important in here is that mechanoreceptors are involved in our hearing and the balance and coordination. All right. So the hearing, as the sound travels in our external auditory canal or meatus, all right, it causes the tympanic membrane to vibrate. And as a result of that, there is a fluid that goes on the run and inside your cochlea, which is the hearing sensory receptors are located. So it's generates by movement of the hair cells inside. Now, if you didn't have that lecture, just understand that the hearing sensation is a part of mechanoreceptors. Similarly, your balance. Next type of stimulus is the temperature, right? So obviously these receptors are sensitive to changes in temperature. If you're taking a shower, for example, you could, monitor and figure out the water is cold or hot before you go in, right? Because you have these thermoreceptors everywhere throughout the body, okay? Next up, you have photoreceptor. These are the sensory receptors that they respond to the light energy. So mostly concentrated in the retina. You probably remember from your anatomy. These are where the photoreceptors are located. Two types of photoreceptors, rods and cones. Cones is for colors. Cone is for clear images. Cone is for central vision. Rods is for peripheral vision. You see kind of like in dim lights, and mostly important in picking up movements, all right? They really work when there's not much light availability. So light intensity, colors, movement, pictures, all of that can be picked up by these type of receptor, photoreceptors. They detect photon. Next up, we have chemoreceptors based on a stimulus type, all right? So these are the chemicals that we can detect in our environment, such as a smell, all right? There are chemicals in the odor, for example, that goes into your nose, all right? And you'll be able to, pick them up and, again, send a signal to the brain, and then the brain can interpret it as a smell of food or a smell of flour or whatever the case might be. Taste is also chemoreceptors. Most of these chemicals, they need to get dissolved in the environment. In the smell, there's a mucus lining, and in taste, you have saliva. All right. So whether it's sweet, whether it's sour, whether it's salty, whether it's bitter, these are the chemicals in our environment and in our food, in whatever you put in your oral cavity, and they're able to detect that. So these are chemicals, so it's chemoreceptors. So there you have it. Those are based on the stimulus type. Next up, we're going to go ahead and categorize receptor based on location. We have two locations. One of the location is called exteroceptors. Extro means exterior, outside. Exteroceptors are the receptors that are usually towards the surface of body, all right? And they're sensitive to touch. So again, based on a stimulus type, this could be mechanoreceptors, same as this one, but we're talking about the location now. So the location of these are towards the surface of the body. So this is the reason why you could detect the slightest thing that touches the surface of your skin, all right? Pain and temperature are the same way as well, right? So some of our special organs have the exteroceptors as well, like photoreceptors. I mean, they're towards the surface of the body, right? So again, you could think about that. The receptors could be way deeper, like maybe in the organ or nearby the organ, and if that's so, the stimulus comes and arises from within the body, and this is called interoceptors. Again, you could think of it as interior, inside, etc. Finding visceral. Visceral means what? Means organ, all right, and blood vessels. Right? So again, they're sensitive to temperature, stretch, chemical changes. For example, maybe you had a bee venom, bee stung you, and the venom goes deep in the body. I don't know if you guys got stung by the bee before, right? But it goes like so deep, all right? So, and you feel like that area, that localized area deep in the body, they're still hot. Sometimes you feel like you have you know, pain coming in from your stomach, or you feel like, you have a headache deep inside your brain, right? So those are from viscera, from the organs coming in from deeper part. That's why it's called interoceptors. Next up, we have proprioceptors. Based on the location, proprioceptors, they're always in skeletal muscle, tendon, joints, ligaments, things in that nature. So basically, they advise the body about your movement. So that way you could coordinate the movement, you don't pull or damage the tendons or ligaments, or damage your joints as you're using them, etc. So those are called proprioceptors. All right. Degree of a stretch. They respond to the degree of a stretch. All right. So if your ligaments keep getting tighter, and keep getting pulled, you have a tendency to do the opposite action because you don't want to hyperextend your hand, for example, movements. Next up, you got classification based on a structural complexity. In other words, what do they look like? So you have two kinds. One is simple, which we're going to be looking at most, or complex. Usually the complex one related to the special senses. They're really unique in terms of what they look like, how the photoreceptors look like. It's no other place you can find that. So it's kind of like unique. All right. So based on the simple type, again, there are two subcategory of them. They are known as encapsulated or unencapsulated. What is that referred to? Is mostly they have like a structures around the nerve. And if they do like a connective tissue, then we call it encapsulated. Meissner corpuscle and Pacinian corpuscles are like that. I'm going to show it to you in a minute. Unencapsulated, when there is just like free nerve ending. There is no connective tissues or structure around the nerve, and that would be unencapsulated. Let's go ahead and take a look at really quickly to see if we can see it a little bit better. Here are a good example of encapsulated. Here's the Meissner corpuscle, here's Pacinian corpuscle. These two types you probably ID'd in the anatomy under the skin, and they are right on mostly on the dermal area, dermis. If you remember, you have epidermis, dermis, and hypodermis. These are in the dermis area. And again, based on their location, there are extraceptors. They are towards the surface on the skin, for example, mostly. And based on the stimulus type, there are mechanoreceptors. So you can see S is for stimulus type, mechanoreceptors, all right? And in this case, we're looking at based on the structural complexity, and they happen to be simple, encapsulated. You will see the structures around it. It looks like a chopped onion in this case. Versus unencapsulated, right? Here's the unencapsulated, right? And you can see they're just free nerve ending. If we could enlarge that, similarly, these are kind of like, there's no extra structures around the nerves, so they are unencapsulated, and that's what they structure, that's what they look like. Where they located, what kind of a stimulus. Now, sometimes you might be able to see nociceptors. Nociceptors, they're a type of mechanoreceptors, but they are associated with pain only. Similarly with the proprioceptors, they're for a stretch, but they're a type of a mechanoreceptors as well. So again, a book could have a topic of physiology. A particular author, like Marib, your author of your book, wrote it. So there are many other physiology books with different titles and so on. And the title is Anatomy, Physiology, and so on. So as you can see, my point is that a particular receptor can be categorized so many different ways. All right. So that's what we went through. All right. So let me see if I covered everything. It looks like I did. There was just like several examples of that. Now, uh, what do we do after this? Okay, so after this, you go from the sensation to perception. In other words, if you recall, all of these sensation receptors, they detecting the stimulus via the sensory neurons. They have to go towards the central nervous system. So the nervous system can actually become aware of the external environment or the things that are around. So that's the job, perception, integration, all of that is the job of the CNS. All right, adaptation. Whenever the receptors are being stimulated repeatedly, sometimes they become less responsive. That means they may not work as well. And this is called adaptation. All right. So adaptation actually occurs in most of our receptors. I'm going to give you an example. In chemoreceptors, adaptation, like sense of the smell. If you go to the kitchen, for example, somebody's cooking something, you could smell the food. But being there for like 5 minutes, you won't smell the food anymore. What happens to your olfactory senses or the sense of the smell? They became adapted. All right. Let's say you're studying and the background noise of the TV, somebody family member is listening to the news and so on. It might bother you at the beginning, but after listening to it constantly, you might actually feel to ignore it. All right. So again, to some sense, they become adapted a little bit as well. Taste. Let's say, the food is ready. You're tasting it. It's very spicy, but after eating it a little bit, it may not be as spicy, or it may not be as salty because you get used to it. This is called adaptation. All right, mechanoreceptors. One of the major capability of adaptation that occurs is our mechanoreceptors. You put your clothes, you put your rings, your earrings. You feel that object is touching your skin and so on. All of that is happening. So, but very soon it's like part of your body. You don't even feel it anymore. These are all adaptation, all right? So, again, two things. Adaptation could be in, dark light. So your photoreceptors, they're, subject to adaptation as well. If you go to a dark room, all of a sudden from area that was really light up, your eyes need to get adapted, all right? And it will. So to understand this part, your receptors are being stimulated constantly, repeatedly, and then they become less responsive, all right? Two of the receptors that they do not exhibit that much of adaptation. One is nociceptors. Nociceptors happen to be for the pain, and we discussed this earlier, right here. Nociceptors for pain. You don't really get adapted to pain. Now, pain or nociceptors could be a type of mechanoreceptors, but we don't get adapted that well. Let's say you were doing gardening and something went into, or a nail went into your skin. It's going to bother you and it's going to be pain for quite some time unless you go and pull that nail out. All right, then probably it's going to be less painful. The idea is that if you get adapted to that condition, all right, then you never attend that pain, and it could lead to infection, another problem. So it doesn't make sense to get adapted, because the body wants to get informed about the things that we're doing and so on. Another one that I could think of is proprioceptors. Proprioceptors are, remember, proprioceptors are for responding to the degree of a stretch. So again, these are mostly in joints, in ligaments, and your ligaments, if you pull it and you keep pulling it and you keep pulling it, eventually it's going to get damaged and ruptured, all right? So again, if your ligaments is stretching and so on, let's say you're working out or whatnot, it doesn't get adapted. So, when it gets stretched, it gets tighter. And again, they have a different response. You're not going to get used to it, because if you do, you might actually damage your ligament, damage your tendons, etc. So that does not happen. Interestingly enough, what do you think thermoreceptors are actually, do you think that one is subject to adaptation or not? Thermoreceptors. Detecting heat or cold. To some extent, yes. If you jump into the pool and it's super cold at the beginning, once you're in there, it may not be as cold. You just got adapted, or vice versa, right? You could just put it like a little bit of warm water on a beaker and stick your fingers in there and leave it there. After a little while, you notice like it's not as warm as first you put it in, all right? So yes, thermoreceptors are subject to adaptation as well, all right? So that's the phenomena of adaptation. Next up, we wanted to take a look at classification of the nerve. Classification of the nerve based on mostly directions and whatnot. It'll be either sensory, motor division, or mixed, both. So sensory or afferent division, remember, carry impulses towards the CNS. So again, you have from a receptor via the sensory neuron or afferent fibers, you're taking information to the central nervous system. For example, you are driving your vehicle, all right, and all of a sudden you see the red light. Red light, you see the red, your photoreceptors detecting that information is going to go to the brain. And again, on the visual association area located in the occipital lobe, you're able to, interpret that as, you need to press down on the brake. Red means the stop. Via the motor division, the impulses or efferent fiber, E for exiting, A is for arriving. This information or the impulses exit from the CNS towards the effector organs, obviously. So that would be motor. Mostly the effector organs would be your muscles and glands. So at this point in time, red means a stop. So information got out of the central nervous system, reaches your muscles of the legs, and as a result of that, you step on the brake. All right. So sensory and motor fibers carry impulses to and from the CNS. This is most most common type of a nervous system. So this is mixed, like when we're talking about the both of them together and so on. All right. So the mixed nerve, you can have either somatic, the ones that we have control over it, or autonomic, the ones that automatically happen. So somatic afferent, information is coming in. Somatic efferent, information is leaving. Again, we have conscientious control. This could be towards the skeletal muscle, for example, that we can, the good example of that would be an example of seeing a red light and you stopping. Visceral afferent and visceral efferent. Visceral means organ. Now, it could be different things now. Visceral afferent, take a look at the chapter 14. You may get a little bit more information about this. But let's say all of a sudden your heart is increasing in rate or decreasing in rate. Or, there's a smooth muscles of the blood vessels changing in terms of their diameter and so on. It's a similar ideas, except that you're going into the organ, it's information coming in for the organ. Let's say your stomach is upset, is moving, information is coming in from the stomach into the brain. You can interpret that your stomach is being upset, and as a result of nerve firing back to the stomach, your stomach might be rumbling or making movements or even sometimes sounds. All right, so that's the idea on the peripheral nervous system. Let's go ahead and take a look at reflexes. Reflexes, we can generally categorize it into two types. One is inborn, or you are born with it. This is also known as intrinsic, or it could be learned or acquired. All right? Learned and acquired require previous experience. Many of the athletes, they know how to dribble the ball. If we're talking about, like, basketball players or soccer players, martial art, these people, they have very quick reflexes for whatever they do. Whether you're, hitting the ball with your racket, if you're playing tennis and so on, these are acquired. You're not born with it. Okay, you need experience, you need practices, and that's what they do all their life. I'm talking about top-notch athletes. As far as inborn or intrinsic goes, you're born with it. All right? If you touch a pot that is super hot, you let go right away. You didn't need to have experience regarding that. It happens automatically. All right? So intrinsic means we are born with it. Okay? So again, it involves only the peripheral nervous system and the spinal cord, or it could involve the higher brain function as well. All right? So we're going to talk about the reflexes and the component of the reflexes and a good example of a reflex. So let's go ahead and take a look at reflex arc and 5 components of it. One, you should have a site of a stimulus, which is the receptor. A lot of times it could be proprioceptors, it could be a mechanoreceptors, it could be rising either towards the surface or within, and intro or extraceptors. But anyway, this is site of a stimulus. So when you do a knee-jerk reflex, if you ever went to the physician, they probably tap your patellus tendon with the rubber mallet and they look to see if you did a knee jerk or you kicked kind of your leg forward. This is a good example of it. So sensory neuron is next. The receptors communicate with the sensory neuron. Sensory neuron takes this information towards the central nervous system, most likely the brain or spinal cord. Integration center, making a sense of things. Again, there could be monosynaptic, that means only one nerve with another can communicate. Here's one nerve, here is another nerve, that's monosynaptic. Or it could be polysynaptic. Example of polysynaptic, again, they could communicate with, again, look at the neural pool, you'll see it. You could have many different areas and so on that they're communicating with one another, all right? Or similarly, they could have many inputs, one output, or vice versa. Anyway, polysynaptic means that they have many synapses. Right here is a synapses. There are many synapses that they are communicating with. The next one is a motor neuron, information exiting the central nervous system. And then finally, you have the effector, which is pretty much the muscles and the glands that we've been discussing as well. Let's take a look at this scenario. It looks like a nail went into the skin. All right. Here you probably have a certain type of receptor, pain receptor, detecting that. This is probably nociceptor. Here you have a sensory neuron. That's number 2. Number 3 is integration center. In this case, the pain is going to the spinal cord. Via the interneuron, it goes from one area to another. And then communicating with the motor neuron. That's number 4. All right. And number 5 is the effector. In this case, your skeletal, your leg, if you're stepping on the nail and you're taking your foot off of that nail. All right. So was this, you think, inborn? All right. Or was it something that you learned through experience? For the first time, accidentally you step on the nail. What do you think? All right. What do you think? What kind of receptor do you think this one is? Is it learned or acquired, or is it inborn, intrinsic? You can pause the video if you want to see if you guess right. All right. Correct. It is inborn. So if you had that, congratulations. It is inborn. You do not need to have experienced this before. Object is painful, right away you take your foot or your skin away from it, and that's what will happen. But let's go back and just like a little bit have fun with this, and to reiterate what we learned, we could simply talk about the receptor now. I wanted to use this as an example of what we've been discussing. So detection of the pain based on a stimulus type, where would you put that in? All right, so again, pause the video and go back to this particular slide to choose from. These are all based on the stimulus type. Which one of these apply when you step on the nail? It's mechanoreceptors. That's right, mechanoreceptor. Is it thermoreceptor? Not really, because you don't, the scenario doesn't say like, you felt the nail being cold as it penetrating through your skin. So it can't be that. It can't be photoreceptors. You're not looking at it. All right. You accidentally stepped on it. And it's not chemoreceptors either. I mean, the smell and the taste and changes in blood chemistry, oxygen, carbon dioxide, things in that nature are chemoreceptors. This is none of it. Right, so it'll be mechanoreceptors based on the stimulus type. Same scenario. Can you guess based on the location? Where could it be? You have these to choose from: extraceptors, interoceptors, and proprioceptors. Which one do you think this scenario would be? Well, it looks like it's towards the surface of the skin, so I would put it under the category of extraceptors, all right? It's towards the surface of the body, all right? So that's what I would categorize this as in terms of the location. How about based on the structural complexity? Is it simple or is it complex? Well, we say complex ones are just unique to the special senses, so it's got to be simple. Now, you have two things to choose from. Is it unencapsulated or is it encapsulated? Does this have a free nerve ending or it has, connective tissues around it? So again, in this example, it's probably free nerve ending, all right? We need more information on it, but, those are some of the nociceptors are. And that's it. You categorize this based on all the criteria that we talked about. So that was a good exercise. All right, next up, we wanted to take a look at these stretch reflexes. All right, and I'm going to be using this particular slide. All right, so when you're tapping the patellus tendon with the rubber mallet, all right, this part, is going to go in. So basically this part is the part that gets stretched. So it's pulling this tendon towards the object that is patellus tendon, that is. So there are receptors and sensory nerves in the spindle fibers. So this one right over here in blue, all right, that's your sensory neuron. So first was the receptor. We discussed this already, proprioceptors. Number two is your sensory. All right, that's your sensory, number two. So I'm just going to put 1 and 2. So these are stretch receptors. All right, as this can get stretched in the joints, in the tendons, that would be 1, 2. All right, so integration center, what happens in here? That's number 3. Motor neuron, that's number 4. And effector, that's muscles, that would be number 5. Quadriceps muscle. All right, so information goes to spinal cord, is coming back and triggers the quadriceps muscle, and you could see the arrow, you're doing a knee-jerk reflex. Why is it that we have positive and negative in here? Pay attention, positive and negative in here. And if you look at the key, it says excitatory synapses versus inhibitory synapses. And that's where we discussed the IPSP and EPSP in a previous lecture. So let's revisit that really quickly. Excitatory or EPSP, action potential is more likely to happen. All right. So it looks like this positive right here, the action potential did happen. Why? Because again, on the red one, as you can see, it went to the quadriceps muscle, and the figure in this case is showing you that the person is kicking. All right. So action potential must have happened in order to get to the muscle. In the muscle, we have the neuromuscular junction, and the person is kicking. Acetylcholine is being released. So that makes sense. But what about here? It looks like the first one is excitatory, but the second one is negative. Take a look right here. So this one, again, think about the positive one as some of the neurotransmitters that have excitatory, effect. And think about the negative neurotransmitter that had inhibitory effect. What were they? Do you guys remember? What were some of the inhibitory neurotransmitters? Pause the video if you want to guess. GABA is one. Congratulations. Glycine is another one. All right, and so on. Those are the two that we discussed. But the point is that again, they could open up the chloride ion channel. Chloride could go in, or they could close the potassium. Channels. Now potassium doesn't get out. So again, it can have. It can open up the potassium channel, so more potassium gets out, and you get more negativity inside. So those were associated with inhibition, all right? But let's go ahead and take a look at this. Where is it going? It's going to the hamstring muscle. So when you are exciting your quadriceps, you're inhibiting your hamstring. So you could do the extension, for example, or opposite would be the flexion. So again, we discuss in anatomy, these muscles are called antagonistic muscle. They do opposite thing because one is stimulated, the other one is the other one. So antagonist muscle, all right? And there is a reciprocal inhibition as well. So in other words, sometimes you might actually trigger the other leg not to move or do certain things and so on. So they're just talking about this could be like, when you're stepping on the nail and all of a sudden you lean on the other leg to balance your bodies and whatnot. So that's reciprocal. You do not need to worry about the developmental aspects of the peripheral nervous system. At this point in time, we're not going to talk about the development and the embryonic development and all that. That's kind of like a little bit more complicated. Right now, we're not going to be talking about it. There you have it. These are the important. What I would do, I would come up with a scenario and then think about, for practices, and think about, what do you think those receptors might do? Categorize them. Say, for instance, you are like in an ice cream. If you having an ice cream, all right, go through it based on the stimulus type. What do you think that one is? All right, is it mechanoreceptors? Maybe. Why? Because you're feeling the texture of the ice cream. Is it thermoreceptor? Obviously, you're detecting the temperature. Is it photoreceptors? Well, I don't know. It depends on the question. But if you're looking at your ice cream and licking it, maybe. Is it chemoreceptors? Yes. The molecules inside of your ice cream, as they get dissolved, you pick them up, whether it's the sugar or sweet, whether it has a certain flavor of vanilla. Those are the chemicals that you detect. So these are all based on the stimulus type. Now you can go ahead and take a look at it. You're having an ice cream. Do you think this is extraceptors or intraceptors? I would say it's mostly extraceptors because, again, the thermoreceptors on the surface of your tongue detecting the temperature, right? But if you have like a whole chunk of ice cream, which, again, on this example, it didn't say so, but you're having like a big bite of ice cream and you're swallowing it and you feel like, that cold temperature going through your esophagus. Sometimes people use a term brain freeze or something. Is actually cold things going down your esophagus. Yes, it could be interoceptors as well. Really, you have to pay attention to the scenario to see what is this asking, what type of clues they're giving you, and so on. And in terms of structural complexity, again, it'll be simple, and most likely it will be, unencapsulated, and because it's a temperature changes and so on, and that would be mostly unencapsulated. But I just wanted to give you a scenario. You would think about another scenario that you're doing today, right now, all right? And think about what happens, all right? I'm not going to elaborate what you're doing. It could be a number of things, but I just give you an example to learn how you can apply this knowledge to that example, so you don't fix on a particular and hoping that that example only is going to come up in your exam. Now you're versatile and you could kind of think about any scenario I will give you. So do a couple of practices so you feel a little bit better. And that's all we're going to be doing for this particular chapter. I hope you learned something and enjoyed the lecture. And